So it is a real pleasure to be here, and I do thank you guys for inviting me and including Argonne in this really important discussion. I'll take a slightly different tack. I will try to keep this at a high level, but I also would like to talk a little today about digging down a little into the technology. What are the limitations, not just for discussing lithium batteries today, but what things might look like 10 years from now to actually start thinking about what energy densities or what it would take to approach, for example, the densities that you get in gasoline today, which is, we heard from BP and we've heard from Shell, is a remarkable material. Whoa. Okay, let me come back to the beginning. Somehow it skipped. Okay, so, it's odd. Okay, so I have really three simple messages. First of all, that the technology roadmap clearly shows the potential for the U.S. in particular. I'm going to be a little bit nationalistic here, but shows the potential for us to really grab the lead, certainly in the long term in the context of energy storage. And in particular, today I'll focus a lot on compact high energy density, meaning transportation. It's also an interesting discussion that's happened this morning on grid scale. The second message is that there is a gap between U.S. industry will commercialize now. So if you look at what we're standing up, say, in Michigan with A123, which is an outstanding company, JCI, Enerdell, these companies that are actually using materials and making batteries, we're very much focused on current generation, and I'll talk a little bit about what that will get us. And we've already talked about this. I'll show this a little more. The cost of that is not yet competitive. What you can still buy overseas, and that's a big issue. And the question is, what do we need to do to overcome the competition? And in the end, it's probably doing what we've always done very well, which is innovating next generation and future generation types of systems. And the last thing I want to say is certainly a plug, but throughout what I'm going to talk about, in fact, I hope to finish this, and I would like that to be the conversation of today, which is how do we work together, industry, labs, and universities, to recreate an ecosystem that no longer exists in this country. I came from Bell Laboratories, and that's a place where there was the total value chain from going from basic research where the transistor was invented all the way up to delivering on a communication system. And the question is, how do we recreate that in the environment we're in today? And that's a very complex question, which I know a lot of you think about, but I'd like to talk about. So here's a plot. You've seen similar things in the last two talks, just slightly plotted slightly differently. This is just theoretical specific energy, which you think of, when you think of specific energy, you think about range of, for example, a battery in a car, how far can the car go, versus practical specific energy. But the real point here is that we're talking a lot about the technologies down here. We're talking about lithium ion or nickel metal hydride or lead acid batteries. And those are delivering today the kinds of things, for example, a 10-mile hybrid electric vehicle. Very important technologies to deliver, but even the theoretical maximum limit on these is something like 500 watt hours per kilogram, which, as you can see, doesn't come close to this magical stuff called gasoline. The stuff is really impressive, okay? So you can start thinking about automobiles that run on batteries, but we're really nowhere, we're at least an order of magnitude away today, even if we can improve from the 100 or 120 where we are today at state-of-the-art lithium-ion batteries to get to something which is 10, 12, 13,000 watt hours per kilogram. It's a huge leap, and so therefore that's why I'm excited about it. It's good science, good technology, good engineering. I say there's a factor of 10 or 20 here. If we go to all electric vehicles, remember we're going from engines, combustion engines, internal combustion engines to motors. Those are lighter, so maybe you don't need quite a factor of 10. As you improve the batteries, you also improve the ability to make smaller and more compact motors, and so ultimately they meet in the middle somewhere. Probably the middle is somewhere in here. And so what I'll talk about today is I'll talk a lot about what we do in lithium ion, and I'll also talk about future generation technologies, but I really want to highlight the challenges to getting there. These are non-trivial. I compare lithium air and lithium sulfur, you've heard about these two this morning, to methanol, and methanol also is good stuff. It's high energy density in those hydrogen bonds are high energy density, just like an octane. Just for fun, we put up wheat. This is just, if you take a pound of wheat, this is the kind of, yes?
Where's hydrogen on all that?
Well, hydrogen actually, so liquid hydrogen fits in, it's basically a liquid fuel. It fits in similar to methanol. It's not it's got reasonably similar energy density. I just didn't put it up here, but you could put it up here. Well, the challenge, the challenge with hydrogen, of course, is producing it and storing it. So I don't know if you've ever driven a hydrogen car. I drove a BMW car, which was liquid hydrogen, a combustion engine. So basically, minor conversion of a combustion engine, but you had a tank of liquid hydrogen in the back, right? So the question is not safety is an issue, but not a terrible issue, but it's how do you get that stuff. So you'll see as this talk goes on where I fall on this. So one of the things that we've been doing in the last few years at a couple of the national labs, you heard about Sandia, you heard about NREL, We work very closely with Lawrence Berkeley Labs, and we've been focusing on trying to think of ways to go from basic to applied, even out to basic to applied and deployment a lot. And so we started to develop what I'd say is a reasonable roadmap for where we think the environment is right now. And so this is I apologize for all the words here, but I'll go through this. I think it's important enough. When you think about the short term on a roadmap, an energy storage roadmap, and again, I'm focusing mostly on transportation-based type of solutions, and you think about lithium ion, today, the 0 to 3 year perspective is that we're going to use commercial materials and commercial processes, things that exist already, and you heard about some of those today. The benefits of doing this, of course, is we know the technology, we have the materials in hand, they're used in laptops, they're used in telephones and small applications, they're not yet used in automobiles fully, but getting there is not so difficult to think about. If you think about the Tesla car, which is built just up the road, that car has 6,000 laptop batteries in it. It's basically a battery with a couple of seats in it. That car is, if you've ever driven one, they're really impressive. Talk about torque in a direct drive engine. But the point is that technology is out there and we can start using it. And it's sufficient for current day PHEVs. By that I mean these are sort of 10 to 40 mile PHEVs. So these are not getting to where Americans would be happy, but you might be happy if you're just driving around in the city of San Diego. The barriers are still high capital investment. We don't have manufacturing here. Again, I'm taking somewhat nationalistically here. And the number was already mentioned today, I believe, by John, which is that the cost today, capital investment, is huge. It's something like $15,000 to $20,000 for the battery in a Tesla car. And presumably for the Leaf car, it's going to be something on the order of $10,000 to $12,000. But it's about it's about $1 per kilowatt hour, just to give a sense of what we're talking about. That's power, okay? What we'd like to get to is something like a third of that, and we're just not there yet. So the question is, even in the roadmap, how do you do that today? I'd love to hear from you guys. This is just what we've been thinking. To do that, of course, you need to, if you saw the chart that was shown earlier, the cost of making a battery a lot of that is in the manufacturing. So one can imagine innovating in manufacturing processes, something we're actually starting to do at our labs. We have recently gotten funded and we're getting future funding for doing things not to do manufacturing. We'll never do manufacturing, but to do things like piloting manufacturing plants, to think about ways not just to make the material, but how do you start scaling materials and making batteries, things like prismatic cells. So the possibilities are here to make this number come down to this number through things like these prismatic cells. That's just going from a round battery to say a rectangular battery, just packing density of the battery, same battery. There are challenges in making a rectangular battery because you have corners and you have all these chances of shorting and all these materials issues, but it's doable. So that's 0 to 3 years. 3 to 7 years is still working on the same concepts, lithium ion. And I'll show this again later in a chart. Lithium ion is about a third of its theoretical value. There's a lot of engineering, materials engineering that still needs to be done. And I'll show you some of the stuff we're doing at Argonne to get from, let's say, the 100 watt hours per kilogram up to the level we're starting to maximize its usefulness. That's still a factor of 10 away from where we are with petroleum, but it's still getting closer. To do this, we'll still need new materials, and you heard that this morning, that the materials we have today just don't get there, and I'll talk about that in a few minutes. But the possibilities, and I won't go through all the details here, but the possibilities to discover those materials are at sort of the tip of our tongue. We know how to get there, and we're working on them, but it's going to take some investment, and so that's the 3 to 7 year horizon. We do need this whole idea of materials, and that's really what my lab's about, is electrode and electrolyte materials and their interfaces. So it's not just the materials, but that interface where we heard things like the gases form, where oxygen runaway type things happen, where explosions happen. The interface is crucial to protect the interface so the electrolyte doesn't essentially catalyze against the electrodes. Those are all very important things. And if we could do all this, which we think we can on paper anyway, then we're talking about getting to factors of 2 times the present performance. Right, so the overall sentiment that we have at Argonne and Berkeley is that lithium-ion batteries are merely a bridge. They're not going to get us to that petroleum. They're just not going to get us within a factor of 10. Maybe within a factor of 10. And the question is this enough? And besides which, a lot of the technologies that we're talking about is already manufactured, or manufacturability is already there overseas. So if we're talking about trying to stand up manufacturing here in this country, that's a challenge. I do want to say that the DOE recently invested in in process innovation. So if you look, there's now a bunch of companies, A123, some of the other companies have set up or setting up plants in Michigan, close to the automobile industry, and there is a lot of activity. There are hundreds of $millions recently got invested out of recovery money to try to stimulate this kind of work. So we will see these kinds of lithium-ion batteries in automobiles very soon, but the issue is going to be really, can we really wring another factor of 2 or 3 in cost out of the manufacturing component of that? And then, of course, the thing that we focus a lot on is the long term. And for the long term, we're not going to be able to use standard lithium-ion. We're going to have to go to whole new systems. We're going to have to change the chemistries entirely, and that means a whole new set of systems, a whole new set of materials, a whole new set of electrolytes, electrodes, and systems, packaging, as well as power electronics. And this is where we really focus a lot, and I'll talk a bit about this toward the end of what I'm going to say here. But the idea here is that we think there are technologies out there that can get you to factors of 10 from where we are today, improve dramatically, substantially different types of systems. The biggest risk here, of course, is safety. Once you go to these very high energy density systems, you also have control issues, and you worry a lot about the things that we heard about in the last talk, where you talk about the safety issues. But we think, at least at Argonne and Berkeley, and of course we talk to companies like JCI and 3M very, very much, we think that this is a way to leapfrog, if you will, from a technology point of view, and own the technology in a sense, the U.S. ownership of this technology. Now, lithium air and sulfur and the lithium sulfur are going on everywhere, the kind of research. But we have more focus than any other country in these areas, mostly through the auspices of the Department of Energy. There are a lot of difficulties, and I'll talk about those. So I'm going to go through these quickly. You guys have already heard this. This is just a sort of a high-level summary. There's lots of ways to store energy, as you know. We've heard about some of those. There's a question? Yeah.
Just a brief question on the previous slide.
Yeah.
The 5 to 10x storage capacity game changing, how do you calculate that threshold? I'm guessing that has to do with market acceptance.
It's market acceptance. It's just thinking about, actually the benchmark is always going to be petroleum, right? So we're accustomed to having an automobile that can fill in 10 minutes or 5 minutes, and that can go 400 miles. So it's range. So if you look at the standards being set, at least the DOE, which is Freedom Car, so they had a set of these standards. They're going 15, 40, 100, and then 400 miles on a single charge, and so that's where we're talking about game-changing being this kind of technology. A factor of 10. I mean, we can debate the factor of 10 versus 5 or 6, but it's clear a factor of 2 is important, but it's not it's game-changing. I mean, having a 40-mile car means you have a smart car, and that's very valuable. But to make it game-changing and really be adopted fully across the spectrum for both light trucks and automobiles, you need that factor of 5 or 10.
Comparable with current performance.
For current performance. So that's really the benchmark. So we've heard about these, so as I said, I don't have to say very much. The hydroelectric, of course, is for the capacity, but I just want to point out in the kinds of things we're talking about here for compact, high energy density, we heard a little from BP about energy storage on the grid, but and something I asked a question about, which I'm very interested in, is solar fuels. When you think about storage, we're mostly thinking about electrical storage. When you start thinking about fuel cells, it's more chemical storage. And then you can be even more clever about using sunlight to convert sunlight directly into liquid fuels. And we had that discussion before. But actually, it turns out that there are huge barriers here, too. Again, it comes back to chemistry. It's catalysis. But we certainly believe, in some of the national labs, believe that solar fuels is a real potential as a way to store. Yes?